Good morning. I am B.B. Mittal. I have been working in this nuclear power corporation. I have spent around 40 years. We have been talking about the nuclear power for a very long time. In fact, our forefather, the great visionary Dr. Homi Bhabha, has very clearly thought of that nuclear power is going to be a must requirement for Indian nuclear energy. Today, we are at the crossroads actually. In fact, it was thought that by this time, we will be coming up with a very big nuclear power in the... But it has not happened so. We all understand, we have been talking about the carbon imprint, we have been talking about that the fossil fuel is limited in the country. We have been talking about that the fossil fuel has to be. In fact, one of the IPCC report, that is the Intergovernment Panel for Climate Change, has indicated that by year 21,000, we need to go for no fossil fuel use. Whether it is possible or not possible, it looks very, today it is looking very difficult. But definitely it all calls for a greater contribution of the nuclear power. Today we are hardly 2% in the nuclear power. We have been having ELWR schemes. In fact, as far as India is concerned, we have thought of that we have got good evidence of natural uranium, we have got good thorium. Of course, the natural uranium is limited. It was thought of that the natural uranium can sustain about maybe 15,000 to 20,000 gigawatt. Today we are finding even that is not possible. But probably still it is possible to go for around 10,000 and 12,000. If we have to really go big way, as far as the nuclear energy is concerned, we have to go for the thorium route. And thorium route is quite far away. So first we have to depend upon our natural resources, natural uranium, by which we can go up to maybe 10,000, 12,000. Today we are at the crosshead of only 5,700 meter, which we have achieved very less as our forefather has visualized actually. So if we do that, and which we need to do that, but in case we feel that we have to be dependent on the nuclear power, definitely we have to cross over to this phenomena, because this is the natural uranium can be converted into plutonium in this our thermal reactors, and then this plutonium which is being converted into from this natural uranium can be used into the fast breeder reactors. And then when we cross over that stage, probably we come to the issue when we can use uranium, this thorium in abundance. So definitely we can say that nuclear power sustainability is possible. If we cross over this route, we have to expedite our power generation on the natural uranium front. We have to go for the fast breeder, which we are anyway going ahead, and we hope that very soon we will have a fast breeder reactor and many more fast reactors will come, and finally we have to switch over to the thorium. This is what only I would like to say at this.
You are making a presentation overall. We'll do that.
Before the panel concludes, certain action plans we identified. Yeah.
Good morning. With the permission of the chair, Dr. M.R. Srinivasan, Mr. B.P. Raja, Mr. Premal Singh Raj, Mr. P.K. Vijayan, Dr. P.K. Vijayan, Shri Surendra Sharma, Chaudhary. I will be presenting this paper, Present Status of the Nuclear Power. My slides will say something about the present energy scenario in the country, the status of the nuclear reactors as on today, slightly about the past of the nuclear power program, and some futuristic view. Well, I think it will be good to talk about certain important key dates which were important as far as the atomic energy establishments are concerned. Well, 1948, just after the independence, the Atomic Energy Act was passed. In the same year, Atomic Energy Commission
was constituted. 1954, Department of Atomic Energy, who is mainly responsible for all atomic energy activity, was formed. 1957, Atomic Energy Establishment, Trombay, which is renamed as a BRC, was established. Our first reactor, which was the research reactor Apsara, was made available in 1956. 1967 was the year in which the Power Projects Engineering Division was formed. In fact, this Power Project Engineering Division was mainly responsible for the establishment of the nuclear power in country. 1969, Tarapur 1-2 was declared commercial. In fact, Tarapur 1-2 was the first nuclear power plant outside Asia at that point of time, and this was available with the help of the United States, and mainly this was installed to see the nuclear power operations along with the Indian grid. 1984 saw the PPED was converted into the Nuclear Power Board with the increased delegation of financial powers, and 1987 Nuclear Power Board was converted to NPCIL, a public sector enterprise under the Department of Atomic Energy, with a clear-cut view to shift nuclear power to commercial domain. Well, this slide shows the scenario of power in India in 1947 and India today. We can see that installed capacity in 1947, the year of independence, was 1362 megawatt, and per capita consumption was hardly 14 units per annum. Today, installed capacity has grown up to 2,76,783 as per the latest Power Ministry report, and per capita consumption is about 700 units. In 68 of years from independence, we have become the 5th largest producer of electricity in the world. But where we have reached by achieving this? Today also, the 33% of the households still do not have access to the electricity. Power cuts, load shedding to the industry continue to be there. There is a restricted agriculture power supply hours, and per capita consumption of power is 1/3 of the world average. So if we have to move forward, definitely the per capita consumption has to be increased, and for that more and more power need to be generated. Well, this slide shows the scenario of various type of power in India, which is hydro, thermal, renewables and nuclear. And the comparison indicates where we were in year 1970 and today in year 2015. Hydro in year 1970 was 6,383. Today we have come to 41,997. It is around 50% of the total power generation. Thermal power was at that point of time was 7,676. Today we have come to 1,900, 535. It is around 69% of the total power generation. Renewables were 230, and today we have grown up to 36,471, around 13%. And as for the nuclear power is concerned, we were in 1970 around 420. Today we have come to 5,780, which is hardly 2.1%. Integrated energy policy projects a required installed capacity of 7,78,000 megawatt by year 2032 to sustain a growth rate of 8%. This was brought out by Mr. Raja also yesterday in his presentation. Other studies project a capacity requirement of 1,300,000 megawatt installed capacity by year 2050. Well, to achieve this, we have to find out ways. These are only projected figures, but how do we achieve this? Therefore, the nuclear power comes into picture. Why we say that need of nuclear power in India? We have limited fossil fuel resources as per the data available. issues related to deployment of population due to submergence of land in case of hydro. We all know it is very, even though we say there is a lot of uncapped power potential in the hydro, but we all know it is very, very difficult when you go for building a dam. Limitations of solar and wind power. Today we have been talking in a very big way as far as the solar and wind energy is considered. But we know that we depend a lot on environmental factor as far as this source is concerned, and the transmission issues remains with this type of power. Naturally, the global warming, we have been talking about the fossil fuel, and the global warming has been a biggest issue, which is highly debatable today, and we have to really find out ways whether the global warming is to be limited, whether it is a cause of concern or it is just being talked about. Well, increasing electricity requirement to support GDP growth, which is a definitely must requirement, and energy security. So these are the factors why do we feel that the nuclear power is required in India. Well, our forefathers have visualized that how do we go about use of the nuclear power in India. As I was telling that there are two sources, one is the natural uranium and one is the thorium. These two sources were mainly there which were to be used for the use of the nuclear power. So we have gone for a 3-stage program. Stage 1 called for where we use natural uranium as a fuel in PHWR reactors, and this can suffice for 10 gigawatt of electricity. This will produce the depleted uranium and plutonium. This spent fuel can be used as the source of fuel for our second stage of the nuclear power program, which we talk about the fast breeder reactors, where the plutonium can be used as the fuel and thorium can be used as a blanket. And this has got a capacity to go up to 500 gigawatt. This produces plutonium as well as uranium-233. Now this uranium-33, which is produced in the second stage, we need lot of fast breeder reactor to get sufficient amount of uranium-33. This uranium-33 can be used as the fuel in the third stage, which is the breeder reactors, and the thorium can be used as a blanket, where the thorium will get converted into the uranium-33 and it becomes this is the stage where we say, because it is said that the India has got 33% of the thorium of the world capacity. So in case we can achieve this, which is an ambitious program, definitely it can go a big way as far as the Indian nuclear power, Indian energy resources are concerned. Well, I will talk something about NPCIL. NPCIL is an organization which is responsible for siting, design, construction, commissioning, operation, maintenance, waste management, renovation and modernization, upgrades and plant life extension. It is in one single company is responsible for all sort of nuclear power management. Well, this indicates the status of various reactors in our country, the reactors under construction, and the sites which so far we have thought that these sites are suitable for installation of the nuclear reactor. The green thing indicates the stations which are under operation. I will just go. First site is Rawalbhatta site, where we have got total 5 operating stations now. One is Rajasthan 2, which has got a 200 megawatt capacity, plus Rajasthan 3, Rajasthan 4, Rajasthan 5 and Rajasthan 6. That is 220 megawatt capacity, total 4 reactor. One of the units, Rajasthan 1, is under long shutdown and for several reasons, and it is under part of DI today. Then another site is Kakrapara in Gujarat, where we have got 220 megawatt reactor. Then we have got site at Tarapur, where we have got the oldest reactor and the largest capacity reactor. That is the 2 reactor of 160 megawatt capacity plus 2 reactor of 540 megawatt. Then we have got a Kaga site, where we have got 4 reactors, which every reactor has got a capacity of 220 megawatt. Then we have got the site, Narula site, where we are operating 220 megawatt 2 reactors, and then Kalpattam site, where we are operating 2 reactors of 220 megawatt, and Kudankulam site, where we are operating 1 reactor of 1000 megawatt. So this makes the total operating capacity as on today 5,780. Then there are certain stations under construction. At Rawatbhatla site, 2 stations of 700 megawatt under construction, which is likely to come on bar somewhere in year 2017 or 18. Then we have got at Kakrapara 2 reactors under construction, again of 700 megawatt capacity, again likely to come on bar around 2017 or so. Then we have got Kalpattam, 1 fast breeder reactor of 500 megawatt, which is likely to come shortly on the bar. And we have got Kudankulam, 1 reactor, 1000 megawatt, which is likely to be commissioned maybe some 5 to 6 months within now. So totally it makes 6 reactors which are under construction and which are likely to be commissioned by something like year 2017 or 18, which makes our this capacity 4,300. So 5,780 plus 4,300 will be the capacity of nuclear power somewhere in 2018. Then this yellow thing indicates the future sites which has been decided. This is the Gorakhpur site in Haryana, where there is an ambitious plan of going ahead with the 4 reactors of 700 megawatt. Then Mahi Banswara, Rajasthan, again 4 reactors of 700 megawatt. These are all indigenous reactors. Then Chhaya Meethi Virdi, Gujarat, where we plan to have 6 reactors of 1000 megawatt. This is the US design. Then Jaitapur, Maharashtra, 6 reactor, 1650. Kaiga, Karnataka, 2 reactor of 700 megawatt, again indigenous efforts. Then Bhimpur, 4 reactor of 700 megawatt. Chutka MP, 2 reactors of 700. Haripur, West Bengal, 6 reactor of 1000 megawatt. Kavda, Andhra Pradesh, 6 reactor of 1000 megawatt. And of course Kudankulam, 4 reactors of 1000 megawatt. So this makes around 36,000 megawatt of capacity with the indigenous as well as the imported reactor source.
So what is the lowest and the highest tariff?
Lowest and the
Highest tariff.
tariff. Lowest tariff is around of the range of 1 rupee per kilowatt
94
hour.
paise.
94 paise
94
exactly.
Tarapur,
That is Tarapur
1 and 2
1
is
2.
94.
And I think the highest tariff as on today is 3 rupees 58 paisa
No,
for
386,
our
386,
386. 386 for Rajasthan 56.
No, no, 386 is Kudankulam. Just
Kudankulam 386.
Kudankulam 1 is 386. But it's only a provisional tariff yet to be finalized.
And I think Rajasthan 56 around 3 rupees 50 paisa around that. So this you can say 4 rupee to 94 paisa.
Yeah.
That is the range actually.
Is there any subsidy involved?
No,
No
no,
subsidized, nothing.
no subsidy.
The
Light-
current, as per the audited balance sheet of the current year, the average cost, if you put it into a basket and average it out, then the cost is working out to 2 rupees 76 paise per.
Well, this question on subsidy, it's possible to argue that the large amount of investment has been made in the research and development area, which amounts to a substantial sum of money, is in fact partly supporting the nuclear power program. And such a view is maintainable. So one can say that that has been a kind of national promotional investment in nuclear energy. But I think if you have a large program of nuclear power, underline the word large, then that investment would not in fact amount to a great deal on a per kilowatt hour basis. If we do not have a large expansion of nuclear power, large capacity, then it could be argued that there is in fact a hidden subsidy.
So it is the levelized tariff for 25 years?
No, we do not follow levelized tariff in the nuclear power.
How do you choose somewhere 700 megawatt? I mean, are there standard size?
We'll come on this question.
Fixed cost per megawatt? Storage per megawatt?
Construction cost per megawatt. We have varied from 5 crore per megawatt to now it is going up to how much, sir? Now
It is 14 point. The
14.5.
latest sanction. There are two separate, you can say, entities here. As far as the domestic program is concerned, the 700 megawatt, the latest approved, cabinet approved one is what is called GHAVP. That is in Haryana, Gorakhpur, Haryana. That is 14.94 crores a megawatt. 14.94.
per megawatt.
So 15 crores a megawatt. 15 crores.
However, you must also look at the fact that there is a long history. Our first heavy water reactors were designed and built in the 80s and then mid 80s, 90s and so on. So if you take historic costs, they'll be much lower. But the point to note is that invariably Indian design and Indian built nuclear power units are much cheaper than those that you can get from anywhere else. The only comparison we do not have is with Chinese origin nuclear power units, but even there, from published information, we can say that our own nuclear units will always have a lower investment cost. This is because of the fact that it's a very high level of localization and the fact the industrial infrastructure has been built up, we are able to hold prices down. The real issue is how we are going to finance the large expansion we would like to have, because the fact of the matter is at any given point of time, investment in nuclear power is more than 2 times the investment in coal-based power. So therefore upfront investment is involved, and then how do you arrange for that? So this is a big question. We can address it later.
3 times, and what would be the tariff we will get for 15 crores per megawatt?
Yeah, the tariff which for Haryana is the range of around 6 rupees 39 paise. In the year 21-22.
But what is responsible for making it 15 crores? I mean, you have so much of indigenous development.
Well, you must understand one thing.
Backloaded tariff.
What is this?
Front loading.
Front load.
Front loading, not back.
Well, you see, the reason it's 15 crores is simply because nuclear power stations got many more systems. It uses expensive material. It uses expensive engineering, expensive manufacturing processes. So it's a very high technology. It's like saying you compare an airplane cost to the motor car cost. It's that kind of comparison.
Engineering over a period of time is now understood. And so, are there any new developments in engineering?
Well, although we all say, yes, we have understood, and now there's a degree of stability and all that, it is still an evolving technology. Not that it is not adequately understood, but certain new aspects can always come in. I mean, I'm just going to give one example, more not to confuse the issues. For instance, we're making all these special materials in India. One of them is an alloy of zirconium using niobium as an alloying material. Now we switched over to some major components in the reactor using this niobium, and we started making that alloy and also making the end product, the coolant channels as they're called. Now what happened at that point of time, we switched the decision to go from an earlier alloy to this particular alloy. Our schedule considerations warranted that we could not complete the reactor in the time frame we wanted to, because our zirconium niobium production was not going to keep pace with the expected timelines we wanted. So we imported some from France to prepare to supply. Specifications are identical, but the manufacturing process in the two shops are such that the end product that we are having is showing big differences in behavior. By that I mean this the zirconium tube made in the Indian shop in Hyderabad let us say, and the radiation remains this long. The same zirconium, same specification, produced in France and then made tube in India for similar, exactly identical radiation is grown up to this much. There are issues that are still not adequately fully understood. Of course, the conclusion to draw is do not mix, but we have to mix at that point of time. And as a result of mixing of these tubes, what has happened is an unexpected replacement of tubes is required to be done on some of these units, which is adding to downtime and all that. So, that is one issue. The second is, in power technology, even if you take a historic look, even in thermal power, it takes 20, 30, 40 years for the technology to mature. Even you take the case of supercritical boilers. The very first supercritical boilers were designed and built in 1950, 1960. But it was about 1980, 1990 before large numbers were being built. Again, you have to understand the behavior of the high temperature materials on a long time basis, its erosion problems, the kind of pulverized fuel burning, all kinds of things. So I'm saying, in general, if you take a broad brush treatment, all energy technologies have a bit of a long haul. And once they are established, they survive for a very long time. So having said all this, let me also say the other good points that have arisen. A reactor installation that was ostensibly designed for service for 25 years. It has turned out they are surviving for 30, 35, 40, 45, 50 years. So therefore, the generation cost in the subsequent years are really coming down very substantially, because in essence you have written off the investment altogether and you are only essentially paying for the running cost. And therefore, they are turning out to be very economic. So both sides are there.
So, some small point. You said that the was manufactured outside. Now, don't we give a proper specification that the coefficient of expansion must be defined? What you want?
No.
How do you
Look. The radiation behavior of materials is a new science altogether. It was just not there in the earlier days. How much radiation, which particular alloy, what kind of behavior, because of grain size, grain structure, trace elements. We have gone through this in many areas, but it's still, there are a lot of new problems that are coming up. But technology also has grown to the point that we are able to tackle those problems. So there are still it's like aircraft, for instance, when the Comet aircraft were built, people knew that there was a thing called fatigue. But what they did not link up was that if you had designed the window in a particular way, in a shape, that one particular design of the window is more prone to fatigue failure than some other kind of window design. Basically, stress concentration in those days was not understood adequately. Later on, when the crashes happened, one understood. So, frontline technologies have this kind of problem. But now, on this question of cost, what is important to mention is 15 crore per megawatt is still a very good cost. Now, the Russian cost for the Kudankulam 3 and 4 is 20 crore per megawatt. But it so turns out that because the fuel in the case of the Russian reactor has a much longer residence time in the reactor than the heavy water reactor has, both these options will give us 6.5 rupees per kilowatt hour in 2022. And that is an acceptable number for that point of time. Yeah, please proceed.
So anyway, I was just talking about the NPPs in operation. Total out of 21 reactors which are under operation, the 2 reactors which is Tarapur 1-2, which is a different type of reactor, it is a boiling water reactor. There are 17 pressurized heavy water reactors, out of which 1 is under long shutdown, which is Rajasthan unit number 1, and 1 unit which is under operation is PVR type, it is Russian design, which is operating in NPPs under construction are 4 PSWR.
Now, are we confident about PSWR? We can solve it.
Definitely. Definitely, absolutely.
Well, in fact, India has got the largest cluster of PHWRs anywhere in the world. Our number has overtaken Canada also. Canada was the original developer of this line. But of course, Canadians have built more of the larger capacity than we did, because earlier on, our problem was our industrial infrastructure was not strong enough to go in for the big size. And then again, we had to also make all these special components of larger size. It has taken time for us to learn. But now we have a mature heavy water reactor technology.
Sir, if I can add to that, he just had the COG, the Can-Do Operator Group meeting about 15 days back. The Canadians had come over for the annual meeting, and they were very, I mean, they had gone around and seen, especially Tarapur 3-4, and they were so much impressed that they have now come out with a proposal saying that India, Canada, the COG, we form some sort of a group, and we think in terms of exporting these reactors to third countries. And the proposal right now is up to 700 megawatts, that is 220, especially for countries which do not have a large demand. 220, 540, and as soon as 700 becomes critical, India will be the exporter, and the COG group will be the business group. And anything more than 700 megawatts will be from the Canadian side, especially in terms of equipment. But the major difficulty that we are running into is the Canadians have, since over a period of time, not really done much research as far as the PHWRs are concerned. With the net result, they would still require a lot of support from our side. So this idea has just come about 15 days back, whether we could form some sort of a business group and think in terms of exporting it maybe to third countries which do not have much demand.
Construction time, what you did on Tarapur 3 and 4, are we repeating on other units?
Well, this is a very good question. What happened is, after doing a very good job there in 5 years, from concrete core to criticality, we had expected a similar performance in Rajasthan, Kakrapara 3 and 4, Rajasthan 7 and 8. Unfortunately, what happened is that there was a period of time when Larsen & Toubro's Hazira plant had a long period of labor unrest. That, of course, is now resolved. That was one issue that negatively impacted. And secondly, once we passed this nuclear liability legislation in India, there has been a great deal of confusion in the minds of the suppliers here about the exposure that they may have to provide for in the event of a nuclear accident. Up until 2010 Indian legislation, the framework of the liability is that the operator is solely liable for any nuclear accident. The operator in turn is provided protection by the government beyond a certain limit. The operator is expected to find insurance up to a certain limit that country's laws have foreseen, and beyond that, the country becomes liable for nuclear liability. Now, all our previous projects before 2010 provided full indemnity to the supplier against any recourse against him by anybody following an accident. The 2010 law in India, which was debated and accepted in the background of the Bhopal accident, provided for an additional clause to 17B, which says that the supplier, the operator has recourse against the supplier for very limited issues, patent defect or willful neglect. Only those issues. However, even that, many of the suppliers said, well, look, this is too vague and we don't know what kind of risks we are going to be taking. Then under the laws that were promulgated, we tried to say, okay, let us now do one thing. We will define limits for the supplier's liability. There are two limits which you can foresee. Limit number one is the risk amount. And we said, okay, the maximum risk exposure is the value of the contract with the supplier himself. That is, if I have bid for 100 rupees supply, I can only be liable for 100 rupees, not for 1,000, 10,000, 100,000, etc. Second, if the item of supply has a certain life associated with it, for example, it's a switch gear, it may have 5-year life, or 8-year, 10-year, whatever, then you can only obligate the supplier to cover for that period of time, not beyond that, because that equipment itself would have become obsolete or whatever, and obsolescence takes place. So we thought that these two would help. Well, yeah, they have helped, but then even then finally what happened is, under the Liability Act, we have defined an upper limit of 1,500 crores as the liability of the operator. And so what was done is that we in fact have formed an Indian insurance pool, whereby this pool is able to give risk coverage to the suppliers. Now, there are still a lot of legal quibbles and all that. It is still work in progress. The atomic energy people are trying to convince the industry people that the protection is adequate, etc. So some of them are coming with some new legal concerns and so on. But this debate, virtually what happened is, people who are already established suppliers of equipment in India, we're not participating in any bid for Haryana project, Kalandia and Shield, that is a hold action. We don't know. Our corporate officers say situation is unclear. So that is again introduced a delay element. Now, why did we this liability discussion went on? Of course, it happened in the reign of the previous government, UPA. Okay, that's UPA. But in those discussions in the Parliamentary Consultative Committee, the BJP Varas were even stronger in wanting tighter and tighter provisions. So now they're in no position to say, well, look, I think we made an unrealistic kind of package. Let us do something. Because the tempo of that time was making it tighter and tighter. Nobody bothered whether it's going to be something the industry is able to survive. I have written the actual clauses in the Tarapur agreement, Rajasthan agreement, Kudankulam. So it is a simple, straightforward supplier indemnification. That has been the global standard practice.
Shall we able to repeat Tarapur at the
What?
Tarapur?
No, now 540 have stepped up to 700. Actually, the scantlings are much the same. The reactor vessel size and shield very much the same. But only steam generator has been made bigger and turbine has been made bigger. Okay.
Sir, just one small point.
Yeah.
With the requirement of time, certainly better technology for construction too would come in. And the concept of
construction machinery were defined.
Right.
So whether we can do the same thing at other stations?
I would say that we can do even better, because with better capacity cranes and more modular concept of construction, I'm sure a lot more better alignment tools and devices available. It will be much better than cut down on the time.
Mr. Verma, I think I was just reminded, actually the way we managed to do Tarapur, the two reactors that much faster, in my time when I was still the chairman, what we did was we would do advanced procurement of key raw materials. We require special stainless steel in large quantities, thick plates and all that, maybe some forgings, steam generator, tube sheet forgings, and all these things. So really speaking, before day zero of the project, you must take a commitment in -1, -2 or -3 years for a certain amount of money and place procurement orders for long time cycle materials as key number one. Number two, the question regarding cranes was mentioned. You know, I was responsible for buying the very first crane of 350 ton capacity with a long reach, Kakrapara. You can do that and all that. Yeah, you can do cribbage and carry heavy loads with great heights and all that. that will take 3 months, 4 months, 5 months, 6 months, getting all the available sleepers in the country and so on. Now, some of the key equipment in Kakrapara, from the rail wagon to the location, the steam generator, it took about 4 hours. You took the thing to the steam rail wagon, it was horizontal, it was lifted, vertical, taken to place and put place. So now our NPCL people, of course I'm not only saying NPCL, even I'm quite sure NPCL will do that, they were all very much more for mechanization, concrete pumping, concrete placing, all that mechanization. Fortunately, that has happened simultaneously because construction industry also has really become much wiser. It's not like the old days. You had in Aurora construction. I'm sure you and I are roughly the same generation. I saw a huge donkey train for excavation spoils being removed with some concrete coming in, etc. I have seen Hindustan Construction Company excavation spoils were removed by the RPF donkeys. That was the technology. But now we can do things much faster. And then prefabrication. For example, of course, we're going to some details. We're going to some details. The concrete, the reactor wall is a precise concrete wall, and there's a steel lining. Now, these days, what is done, of course, is that the steel lining is a huge ring, and you attach to that many of the things that require to be attached in place in the shop itself. All these embedded parts and so on and so forth, and then you take that huge ring, lower it, and then you only have one huge circumferential width. So like that. And as we go on, even piping system, prefab and all that is happening.
One project you can do, but if you take so many projects at a time, you may fall short of these high capacity cranes, etc. Have you analyzed that so many things are available in the country, or we are falling short of construction?
No, these huge cranes you have to import, but they are available. I mean, there is no, fortunately, the crane makers want business also, no. Now everything, even crane making must be made in India, I agree, but it was only a question of some cranes, that's okay. Germany will want to supply, Russia will want to supply, somebody else, maybe France, US, they're all making
We
big
fell
stuff.
short of this machinery in our conventional thermal. We started a lot, and then finally, to deal with all those things, it became that the machinery will shift from this station to that station.
Economics justifies that. A high investment crane, you don't just use it to write it off against one project, because after that it's available still. So what we do is that you move it, but then you don't just keep one to go everywhere and hold up everybody's job. We may have to have 2, 3, 4 sets, but they also keep going from place to place. Yeah, please.
So, well, as I was talking about, this is what is the scenario as for the future program type of reactor is concerned. There are two efforts are there. What is the indigenous efforts, and another is the international cooperation. As for the indigenous efforts are there, we have come to the stage of having PHWR of 700 megawatt. So we plan, as I have told, that various sites have been already earmarked for having this 700 megawatt PHWR reactor. Then fast breeder reactor, of course, one is coming up at Kalpakkam. We hope it will come shortly. And then based on that, further fast breeder program has to be taken up. And finally the AHWR. And this is AHWR is the third stage program. So this already, the design is already done by DRC, and probably it will take few years before this comes into the real practicality. As far the international cooperation is concerned, we have been talking about from the various countries. One is the Areva, France, another is the Westinghouse, USA, another is GE Hitachi, USA, and Russia. In fact, this is what is our dream, but it all depends upon how our negotiation goes on and where do we finalize that which reactor we need to be imported. I think our Director of Finance has been more knowledgeable about the field of where do we stand on this issue actually. But we hope that definitely some reactor will come.
No, I think my intervention.
Well, this is the evolution of PHWR, because finally India has been depending mainly on the PHWR so far, and this has been the evolution of PHWR in India. We started our journey with Rajasthan 1-2 in early 70s, and just after Rajasthan 1-2 we came by Madras Atomic Power Station. After Madras, and this was the indigenization. In fact, from Madras onward, the indigenization efforts really started, because there was no Canadian cooperation after the Pokhran blast in 1974, and the Indian scientists started working very hard on indigenizing all the systems and components. And then the phase came of Narora Atomic Power Station, which we call as the standardized PHWR station. There was a marked changes in the design from Rajasthan 1-2 onwards, depending upon the industry requirement, depending upon the safety requirements, and this Narora 1-2 was totally designed by our Indian efforts, and today also it is operating very nicely. Then the phase came of consolidation of our design efforts.
Maybe can you finish in about 5-10 minutes? Because there are others also.
Sure.
And maybe.
So anyway, this is already covered. I need not to repeat it again.
So I think you should now get on to the.
Okay, I will just.
This Tarapur 1 and 2, would we not increase the size on other units, or we left this technology?
Boiling water reactors. See, Tarapur 1 and 2 was an American origin design. Supposing India had continued international cooperation at that time, supposing we did not have Pokhran test in 1974, it's quite possible we might have built more American reactors at that point of time. But that cooperation was just not possible because India wanted nuclear independence, and the Americans would not have gone along with us, you see. So there was no question. See what happened the moment we had the Pokhran test number 1974. Then they suspended all cooperation. They would not even sell us spare parts, no technology, no drawings, no nothing, even for keeping the plant items going. So it is a total breach of relationship with the United States. And fuel which had contracted to supply over the entire length of the life of the power plant, they stopped supplying. Then they informally agreed that France could supply and so on. So it's all old history. And so then once we started building heavy water reactors, then we said, well, we can do things on our own, so why not? But of course, it hasn't yet come to that situation. Fact of the matter is that we have had a serious uranium crunch. We are only producing in India at the present time 400 or 500 tons per annum of uranium. In fact, we haven't reached even 500 tons. Much of it is only, all of it is nearly coming from Jadgaoda. Second uranium mine project in Andhra Pradesh is just now in the process of commissioning. And because of this uranium crunch, our own reactors, which began to operate very well, we could not operate them at high capacity factors. It's only after the 2008 agreements with US, with Russia, with France, Kazakhstan, and more recently with Canada, we're getting uranium. So our own reactors, built our own technology, but put under international safeguards. They are now having enough fuel to run them at very high capacity factors. Indian reactors, not put under safeguards, are still having a bit of a uranium problem because our needs are higher than what we are able to produce in the country at the moment.
Well, now I will just.
Oh, you're hitting that point.
I have come to performance of our reactors actually. That today we are able to achieve high availability factors around 88%, high plant load factors around 80%. Then 20 reactors recorded continuous run of more than 1 year, which is a very, very good achievement. And one of the reactor completed continuous run of 765. This is the second in the world history actually. We have achieved this distinction. And very recently Narora has also completed 517 days. So our operation has become very steady, and we are very, as you said, that how do we be confident about the PHWR reactor. So the performance of the reactor indicates that we are very confident as the PHWR reactor.
You are not available to our grid discipline. You are not able to direct you.
No, but you know, the load following invariably, even around the world, they do not subject nuclear to cycle the fuel in terms of flux or in terms of temperature. And it's not a question of not managing the grid discipline, rather it's the other way. Since these reactors are producing the lowest cost power in the system, because once you have invested the money, the variable cost is very little. I mean, just to give you an example, in the case typically of a thermal power station, the variable cost is of the order of 60 to 65, 70%. And in the case of a nuclear power station, heavy water type is about 20%, light water type is about 10%. So once you put the reactor, it's in the interest of the system to keep it going all the time and not punish it by cycling and all that. However, I must tell you, when nuclear power stations occupy a large fraction of the generation capacity, one example, France, 75% of the total electricity generation in France is nuclear. At that stage, certainly the French had to accept the proposition that not all of those reactors can be base loaded all the time. So therefore, then they started what they call two shifting. That is, on a daily cycle basis, you operate at full power for 2 shifts and at somewhat lower power for the 3rd shift. There is midnight low load period. So, and for that, they have evolved fuel designs capable of standing that two shifting. So you're quite right. When you have a very large component of nuclear, you cannot assure base loading. You've got to think of other methods. But at our stage, when you're only having a small percentage, it's now in the overall national interest to use these things at high output, high capacity.
But at least for future program, are you thinking of putting a design capability in these stations for two shifting at least?
Well, you see, basically, it's a question of fuel design. It's cycling. If you have got, let's say, a piece of pipe which is kept going at 800 degrees centigrade, that's one condition. If you with that same piece of pipe, you switch it from 400 to 800, 400 to 800, 400 to 800, well, there is a thermal fatigue is there. So, it's that kind of situation. The answer in principle is light water reactors can be designed for two shifting because the fact they use enriched uranium and therefore you can have the fuel sheathing of a higher strength which is capable of standing two shifting.
But we are not having light water.
Well, we are having Kudankulam, we had long ago Tarapur. What happened, let me tell you also, long ago, because we are interested in the history also. We had to do two shifting in Tarapur 1 and 2 in the very beginning because low load condition, there is hardly any take us in those days. I'm not talking of 1969, 70, 71. We did that at that time reluctantly two shifting, gave rise to fuel failures at that time. But then technology has moved since then. I'm not talking of 1970s fuel design is different than 2015 fuel design. So two shifting has to happen if you have a large nuclear capacity. But that point of time will come a little later in our conditions. But it's now understood. The designs can be made for two shifting. But then again there are other issues. Do two shift from 100% to 30%, reduce from 100% to 60%. What is the mix of generation you are having? What's the load pattern? No, these are all issues that are evolving and you've got to find solutions.
So as far as the safety is concerned, as our nuclear reactors are concerned, we have already over 380 reactor year of safe operation. No incident of radioactivity release beyond a stipulated limit of regulatory body ARB. And peer reviews are continuously being conducted by international body which is WANO for all our operating reactors. Well, after the Fukushima, because the Fukushima incident became one of the major factors as far as the nuclear industry is concerned, and there was a lot of talk about whether the nuclear industry is really safe. At that point of time, a lot of committees were made in India. The government of India also directed Nuclear Power Corporation to have review of all our operating stations. What are the real safety margins available for our all operating nuclear power stations? So safety of all our plants was reviewed and it was concluded that the existing design is robust, but for further enhancing the safety, several improvements were suggested, which were related to the following. Additional provisions for core cooling, that is spent fuel cooling. See, as far as the nuclear industry, nuclear power is concerned, the safety will be ensured if the core cooling is ensured. So the additional provisions were made after a lot of discussions. Augmentation of power sources, that the power supply should never fail. That is what is the basic theme, as what has happened in Fukushima, that the total power supply failure was there. So a lot of augmentation of the power supply has been done in all our operating stations as well as the new upcoming stations. Augmentation of
Standby power is not available. These are
Well, you see, very briefly put, Fukushima was an avoidable accident. What happened is that, the Fukushima has 6 units, 4 units, and then there's another station B. The 4 units are in different evolution. Units 1 and 2, the early units, they had, in a traditional way, put those diesel generators, emergency power supply, in the basement of the turbine building. And I'm one of the few people who have been in Fukushima and seen it when it was operating. And it's an open beach. All the oil tankages were at the beach, and the levels chosen were based on the information then available regarding tsunami and so forth. And so they're unfortunately low. But the Japanese themselves, subsequent units 3, 4, in fact they realized that something probably had not been done right for the first one, and that put some diesels at a much higher level. Diesel set plus the associated switchgear and all that. And the Japanese scientists themselves had given the information to their own colleagues that the earlier estimates of tsunamis were too low, and higher tsunamis should be expected. Unfortunately, Tokyo Electric Power Company, one of the strongest power utilities in the world, chose to ignore. It is a corporate failure. So what was an avoidable accident became a huge accident, costing the country, costing the industry.
So, and then another very important modification was the augmentation of on-site water inventory and the arrangement for transfer of water from nearby sources. See, that one of the most important thing was there that when such situation happens, we need water for coal cooling, and therefore now all stations arrangements have been made so that sufficient inventory for at least a week after the no power source is available is remaining at the nuclear site, and so that the cooling can be done where all the reactors can be brought under safe shutdown conditions. Then another issue was there, which was the containment venting and hydrogen management. See, one of the reasons for this during the Fukushima, when the fuel meltdown took place and then the zirconium and metal reaction takes place, the hydrogen generation is there. It makes the explosive mixture, and that was one of the main reasons that the roof blew off actually, and the radioactivity got released to the environment. So after this incident, the whole review has taken place, and now phase-wise we are installing this hydrogen management in all our reactors and the containment venting arrangements. That emergency control center facility, that again there was a recommendation, very strong recommendation internationally, that we should have an arrangement at each site so that the people can assemble there, people can work there under high radiation condition to take care of our nuclear stations under emergency conditions for a month or so. So this also arrangements is being made at all our nuclear sites, and then severe accident management guidelines have been prepared after this. Well, then the issue needs to be addressed is for future upcoming station is the land acquisition matter, which is a very, very important matter, which we are facing a lot of problem. Of course, it needs very large resource mobilization for making our futuristic plan, heavy demands on industry, safety related concern, and public acceptance, which is again a very, very important factor, that we can't succeed in our targets until the public acceptance is there. And ideological opposition of certain entities to nuclear energy. So whatever you do, there are certain sections are there which keeps on opposing the nuclear energy. So with this, my presentation is over. Thank you.
So now the floor is open for some comments. Please.
I'm BB Naran, ex-NPCL.
Dr. Srinivasan has already pool is being built up, and with that, certain actions are being taken by which the suppliers will have a confidence that they need not to put the money from there, and whatever the equipment has been supplied, whatever the cost is there, they have to bear that cost only. So that is one bigger issue is there. And then as far the resources concerned, definitely we are working, our finance department is working very strongly to see to it that the finance is made available for our upcoming station. As far the construction is concerned, the question was asked by him also that because we have achieved the construction of EHWR for 540 in less than 5 years, but somehow the same thing is not happening as far as the Kakrapara 3-4 is concerned and Rajasthan 7-8 is concerned. Because certain impediments have been now coming up for the construction of these projects, and we are very sure once these are removed, we will again come back to the original thing and probably we will achieve less than maybe now we have to come to the 4 years things. That is what we can definitely have the capability and we can do that. Provided these, whatever the new problems which the industry is facing are over.
Is anything on the technical front, like VVR are well proven or regulated also, but other like Areva, etc.
I think we are mixing issues here.
Okay. No,
I mean, let me also explain, to answer the basic question you asked. What are the steps being taken to ensure that we are able to complete, if not in time, at least within cost? Okay. You must appreciate that when we floated the tenders for Kakrapara 3-4 and Rajasthan 7-8, the quotations received were as less as 20% of our estimates. It was only about 80% of what we estimated. The main reason was because that was a time when there was a gloom as far as the industry is concerned. And unfortunately it still continues. And the major reason for this is lack of finances. Okay. And today we have very large contractors like HCC, even Larsen & Toubro, which have run into financial problems. How do you overcome this? Let us take a typical construction, this thing as like the reactor building, for instance. It is for Kakrapara 3-4, it is given to SCC. SCC has run into a severe liquidity crunch. But we also cannot tender this out to somebody else when the reactor building is about 60% complete. We have now we have now devised a system whereby we are able to give them some little advances. We are now forwarding money to them. Well, if you ask me whether this is a post-tender change, yes, it is a post-tender change. But then when you look into the overall interest of the project and completion as far as possible with as little delay, we have been giving money to the suppliers. We have also been paying money to the main contractor suppliers so that at least they are able to lift the material. The intent here is to ensure that at least we do not lose much more time. Because if you just look into the delay, the average cost of delay on a yearly basis, an average escalation you can take it as about 7%. And by interest liability in a project is about 10%. We are able to borrow at below market rates. So if we just add up these two, it is about 17% is the damage which we will have by a project getting delayed by 1 year. The intent here is, if we are able to give the money to these people to forward it, and of course we do charge an interest, let it be clear that we are not giving anything free of charge to them, because there are CBC regulations on this. The intent is, we are trying to cover up. And let me also tell you, this has worked out to a large extent. Kakrapara practically is about 76-77% complete, and we are hopeful that we will miss the target, yes, but we are trying to reduce it to as little as possible. So we are able to complete it within the cost itself.
How much time?
17-18. We expect completion, the criticality to come around 17-18.
You see, what has happened is, sadly, it is a matter for reflection. The entire Indian system is riddled with a lot of illogicalities. For instance, the holy cow, post-contractual conditions favoring the contractor. But then the issues are certain types of circumstances that they could really not anticipate. For example, in the case of coal-fired power station, when you based on imported coal, suddenly that country is importing an export cess. I mean, if you're not there, they are needed. What do? So this kind of situation is happening elsewhere also. But I think the real issue is in many areas in this country, governance, because public sector involves government. Governance from the government has become lax for a period of time. Of course, all this is also affected by so-called scams pointed out by CAG here, there, everywhere. And after all, they are all government functionaries. And then, the CBC's impositions on procurement processes, and then the Information Act requirements and requests. All these things, in a sense, are making project management of the public sector extremely oppressive. And therefore it's all very well in public. No, they must give an answer. I mean, those people tell me, the CMD and some of the key people, 30, 40, 50% of the time is CBC and CIC. Nonsense. If you want to progress, can you ever do this? Anyway, now, we'll ask the floor now, because otherwise we will get lost.
One small question.
Please.
Since the accidents have not been there in our nuclear station, it's a good thing, fortunately. I had observed that your attention to the emergency supply, DGCER's design, the flood levels incorporation, and you save, it results into savings of course, but the final flood levels are not kept into view. Similarly, the fire provisions, dealing with fire, segregation of the cables, etc. Attention is not paid, sufficient attention is not paid towards this side, and maybe some of these stations you tend to commission before you really attend to these things. In Narora it had happened.
No, listen. It is all a learning period. Narora, what happened, I'll tell you. There was a turbine blade failure, resonance failure of the turbine blade. That blade went and broke the lubricating oil supply. Then it went taken a fire. It is true, later on we learned a lot of things in segregation of cables, this, that, whatnot. We've been having resonance failure of blades. It's not a nuclear issue, but that's the machine we get from BHEL. What the hell do we do? And then they will say, but look, the grid conditions have been very unfavorable, therefore resonance failure is taking place. Country is learning in all these things. It happened a long time ago. But fortunately, look, now the review process are very tight. The regulatory board has become much wiser. For instance, you're talking of flood levels. I have reviewed the Kudankulam designs because I had to present myself to the public to say that it's going to be safe. I have reviewed every single bit of it. Of course, at the time the Russians and our Indian colleagues started doing it, everything, they have really put at a much higher level. Tsunami, although it may not have been known then, but the Russians said, yes, there is a thing called tsunami. Our international information is this. We must provide for the plinth level to be so and so, so and so, so and so. Then provision against flooding of the diesel generator rooms. It's like a bunker which is completely sealed, hermetically sealed, and then the fuel to be arranged in a particular way, controls for the diesel in a particular way. All these things have been done. So a lot of these things have been done, and I think it takes far too much time in this forum. If people are interested into discussing this, I think it's a good thing. Maybe a group interested should be received by NPCIL and EERB, and I think jointly you should expose them. I think it's a good thing. So if there are enough people who are interested, I'm quite sure our NPCIL colleagues will take the initiative and do this. Because we want you people to understand what's happening, so that if you feel satisfied, you can also explain to other people, look, these people are doing a professional job. That's very important. Okay, other comments? Yes, please.
Sir, my question relates
I think somebody must give him a microphone.
and availability of fuel. Where do we source our fuel from? And what are the geopolitics involved in this? Are there any
Okay.
involved in
You
this?
see, now, I don't know if I should be answering, but I will do so simply for the sake of quickness. You see, we got natural uranium is required for the heavy water reactors. There are two sources, Indian source, imported source. The Indian source fuel for reactors which are not outside safeguards, which are outside safeguards rather. That is to say, there is no obligation on our part to open up those installations to international inspection, and we can do what we like with our spent fuel. Those reactors are continue to have somewhat of a crunch, but it is getting reduced because our internal production is increasing. The reactors that use natural uranium of imported origin, which are under safeguards, there is no problem. We have diversified, certainly, I mean, no question. Kazakhstan, Canada, France, Russia, so there is enough diversity. Enriched uranium for Kudankulam, Russians have contracted to give, but in principle, we can get enriched uranium from the others also, like maybe United States or France, if we wish to. But it so turns out, international market, Russians are having a dominant position in supply of enriched uranium. So supposing we were to build our own enriched uranium reactor, we can get it from Russia or from somebody else. So there is a certain market, but not everybody is there. As of now, enriched uranium is being sold as a commercial product by the United States, by France, by Russia. Okay? Right. Now, I want some of our colleagues in the atomic energy program, of course I am also one of them, we have been holding a view that starting off the small base of PHWR reactors, we can have a big fast reactor program and a very big thorium program. That's only possible theoretically, because in reality a lot of time cycles are involved. So if you want to have a large amount of nuclear power in a short time frame, this route is really not a practical route. So during the 2005-2009 negotiations, I have kept telling the public in India through newspaper articles that the first stage reactors, which will be heavy water or light water, will not be as small as 10-15 megawatts, 10 gigawatts, but much more. In fact, I had then speculated that for the long-term growth of nuclear power in India, we require something like 30 to 50 gigawatts of the first generation reactors. Then, of course, fast reactors and thorium-based systems. Now, the kind of thinking I'm having now is, if you were to have 275 gigawatts of nuclear power by 2052, of that, in my opinion, something close to 100-155 gigawatts would be natural uranium and enriched uranium. Something like 75-100 gigawatts by the fast reactors, and the balance would be thorium-based systems. Because there is a long time period involved in going from one phase to the other phase. It's not a very short time. That's the reason is so-called breeding gain, that is to say the amount of new plutonium that's created is not as fast as theoretically considered possible. So there are practical problems that are there. So I come back to one more very important issue. It's not that we just want to shut our heavy water reactor program at some low level. We will be required to build heavy water reactors in a substantial number. And I am telling internally the commission and all that, don't take commitment for 2 like that. Take a commitment for 10, 12 reactors at one time. Place orders for equipment for 10, 12 reactors, so the industry knows continuity of job is there, and then they get learning curve benefits and cut down the manufacturing time cycles, make it more economic and timely. Second thing, it also appears to me, of course this is an issue that we can literally, although we have been talking a lot with the French and the Americans, unless something were to change drastically over a period of time in the next some months, etc., their costs appear to be substantially higher than what we are expecting. So these discussions are going on. But it's entirely possible that we have to depend on our own. That is more PHWR, certainly more Russian reactors. In fact, President Putin, when he was here last year, he said that he would like to do 10-12 or sell to us 10-12 reactors VVER. And I would think it's in our interest to just get on with them, not just again 2 here, 2 there, etc., but sometime 10 or 12. That is, in Kudankulam, instead of only 2 right now, make 4. and another site where you can have about 6 reactors, get on with it. Because it turns out that they are much more competitive than other people. We know that. Thirdly, an issue that is within the system, not probably the public domain. We already have enough knowledge about light water reactors because we also built these submarine reactors. We have a lot of knowledge on the heavy water reactors. We already have the ability to design our own PWR. And such a PWR of 900 megawatts, it's on the drawing board. It's an internal design.
But light water?
Yes. Yeah. Submarine reactors are light water reactors. Yeah. There's a PWR as a standard there. So, in my opinion, it is probably the best thing to do for us to get on with our own 900 megawatt reactor for the same reasons that organization will be high, and we should see and produce them. So, but this is not published outside the system. I'm just sharing this stuff.
And I would like to speak today on issues in the development of nuclear power in the country, because all of us recognize that there is an urgent need to look beyond fossil fuels. And nuclear is one of the options which one has to look at positively, because you cannot have all your eggs in one basket. It's important that the mix as far as any national policy is concerned, and therefore it is important that nuclear also becomes a key player, or at least a major player, when it comes to the national policy on energy mix. Let us try to sort of list out what are the issues that we are facing in the development of nuclear power. The first one, of course, is the obvious development of the requirement as far as the land is concerned. The requirement of land, especially for nuclear power projects, is much more when compared to any of the other conventional fossil fuels. This is also because of the requirement of the AERB, wherein we have to have various zonings. 1 kilometer we have to leave, that there is a no developmental zone, etc. And more importantly, with the opposition that we are facing today to land acquisition, both initial challenges and probably a very important challenge that we are facing. However, having said this, I would like to bring out a silver lining which has happened in the last, I would say last 1 month. At the height of opposition to land acquisition, NPCIL has been successful in getting land in Madhya Pradesh. The Chutka land allotment, in fact, the government of Madhya Pradesh has already allotted to NPCIL, and probably without much opposition and at a reasonable price. And when I speak of a reasonable price, it is a price at which even the people who are going to surrender their lands are satisfied. And the major reason for this is because of the proactive R&R schemes that NPCIL has got, as far as the CSR programs which NPCIL has been implementing, especially in their project areas. So the first difficulty that we run into is land acquisition. The second issue, of course, is money. As our Honorable Chairman mentioned, money is something which is very much in demand. There is very little money going around. And when one looks into the availability of money in the money market, there are certain norms which are called the Basel III norms. The Basel III norms have not yet become mandatory, but it will become mandatory from 2016-17 financial year onwards, whereby there will be certain limits, electricity, and within that there will also be a subsector, power, and then there will be an entity, in this case Nuclear Power Corporation, and maybe at a later stage Bhavini also will come into the picture. The Basel III norms require that there has to be some sort of a gradient availability of money for the various sectors for development, one. Number two, that the bankers are required to ensure that they do not put all their eggs just into one basket. They have to ensure that the money that they are going to give will lead to some sort of an equitable development of the various sectors. And also to ensure that none of them become NPAs, non-performing assets. So this is the second challenge, and especially when one looks into the front loading which is required for a nuclear power project to take off. Let me give you a typical example. First of all, the cost of a nuclear power project.
I can tell you at least to begin with the latest sanctioned project, which is GHAVP, that is our Haryana project. The sanction is for 20,000 crores. We are going to get 1400 megawatts. The land acquisition part itself for Haryana has come to something like nearly 600 to 700 crores. The R&R activity will go on for maybe another 100 to 150 crores, the R&R schemes. Thereafter, for most of the major equipment, you have to give a 10% advance, which means as much as 2,000 to 3,000, that's about, 10 to 12% of the money is loaded upfront, even before the project really takes off. And please understand that these are long gestation projects, which means they're going to run over a period of maybe 7 years or 8 years, depending upon the market condition as far as the contractor support is concerned. So when one looks at maybe an average borrowing rate of about 10% per annum and something like 3,000 to 4,000 crores carried over at 10%, there is always a tendency that this itself becomes a multiple. So A, the availability of money, B, the sectoral restrictions, and most importantly, the long gestation project places considerable challenge when it comes to funding of a nuclear power project. What is the next option? The next option is, yes, one can look in terms of maybe an ECA or an ECB. ECA, of course, is an export credit assistance. ECAs are generally given only by suppliers whose equipment you're going to buy. And especially for our domestic programs, there's hardly anything that we are buying. Maybe for the 700 megawatts, yes. We are getting the turbines, the 700 megawatt turbine is being imported from Alstom. We did try to get an ECA, but then it was not a very easy process. The paperwork involved in getting an ECA sanction was so difficult. I'll tell you why what happened. Let us take a typical example of Alstom, their TGs. We found that the initial work on the TG was being done in Brazil, or in Mexico rather, Mexico. About 30% of the work is being done in Mexico. From Mexico, after this work is done, the initial casting is done, it is brought over to Poland, very close to Warsaw. And in Warsaw, about 20 to 25% value addition is done. Thereafter, it is transferred to Germany, where about maybe another 15 to 17% work is done. And finally to France, where the billing is done. So when one looks at an export credit assistance, who will give you the assistance? Will it be Mexico? Will it be Poland? You will have to talk to multiple agencies even to get the export credit assistance. The second one is what is called as an export credit borrowing. This is a market borrowing, which on the strength of your balance sheet, you can go down into the money market abroad and try to borrow. NPCL has made efforts. In fact, we have a small ECB of 250 million US dollars. This has been borrowed from Singapore. We borrowed it at something like an average rate of interest of about 4.6 to 4.7% per annum. It's small in terms because it is just 250 million, and we have not hedged it because we thought it was not worthwhile to hedge it. But let us take a typical case where we want to go in for maybe 1 billion or 2 billion in terms of an ECB. The major challenge would be, apart from the interest rate, because for a large ECB, it will not be one player, it will be multiple players. In fact, there would be a cartel of bankers who will come in. So you will have to first negotiate so that you are able to get a reasonable rate of interest. And thereafter, one has to provide for hedging, because post July 2014, the RBI regulations require that any public sector undertaking or even a private sector undertaking, when they go in for an ECB, they necessarily have to go in for hedging. In case they do not hedge it, the bankers are supposed to exercise due caution, especially while sanctioning any further borrowings to these companies. So per se, now we are forced to do this. The third issue which I would like to talk about is industrial capability. Well, we do have the infrastructure, the industrial capability. But the main issue here is, suppose we do not keep continuously placing orders on the industry. What happens is, the accumulated experience that we have in the industry tends to drift away. And as Dr. Srinivasan mentioned, it is very important that we have a program whereby maybe every year or every 2 years, a new reactor is being announced. The reason is that then there is the comfort as far as the industry is concerned that this is an ongoing program, maybe for 15 years, maybe for 20 years. The accumulated experience and the expertise available in the industry could be retained. We will not have people drifting away from the industry. Because if we have spurts of announcement, 2 reactors coming up and then for the next 5 years there is a lull or there is absolutely nothing announced, then what happens is it becomes difficult also for the industry, because you see these are very high investment companies. In fact, we already have created a company which is called the LTSSHF, the L&T Special Steels and Heavy Forgings. This is a specialized company especially for nuclear forgings, and until we are able to place sufficient orders on them, it will be very difficult for the company to financially sustain itself. Be the construction risk, the construction of the nuclear challenge, money which is available. I did mention earlier also that when it came to Akrapara 3, 4 and Raj, we were able to get 20% of our. But having said that, the situation where contractors do not have the money, whether it is HCC, or even L&T, back to you, asking for advances. And as we just mentioned, various regulatory authorities in this country like the CBI, the CBC, the RTI Act, which there are regulations in place that, to shake off. However, having said that, yes, one has to get the project going. So you have to really have a thought process out of the box. And you have to see that while we are able to the project completion period, none of us also personally land up into any sort of a CBI inquiry or a CBC inquiry. It's very important also for us in this. So this is the basic construction risk which we face today. Let me come to the regulatory challenge. I will give you a typical example. Kudankulam 3-4 was approved by the government way back in November 2013. Thereafter in 2014, the design base as ground motion, which is basically for the earthquake resistance, those parameters were changed by a year. Okay, we went back to the Russians saying that look, now the new specs have come in. It will require you to have a relook at the specs itself. The Russians very gleefully looked at it and said, well, we can do it for you. It will only cost you an additional 360 million. October 6th was the day to make this announcement in the presence of our agent. We hear, look, more than 95% of us are in Russia. We made a dollar to ruble rate in the year, and we found that when the dollar is to 32, thereafter, like 54 or 50 a dollar. It's insisted upon look here. We have to go. If we go back to our government, the dollar, you getting 300 charge for you. No, this March, well, I think the 54 it had gone down to 7 ruby. That's the civil liability for post only for new project. We have a major period of liability, maximum amount. NPCIL has already, as per the Act, that the maximum which would go would be either 100 crores or 100 crores liability through the Act itself, which speaks of what is called as the initial licensing period. And the initial licensing period, as per the AERB regulations now, is 5 years. So 1 year anyway you are giving it for latent and patent defects, plus the initial licensing period of another 5 years. So we have told the suppliers that in our contracts we are willing to state upfront that the period of liability will be limited to a maximum period of 6 years, not beyond that. Which means that the maximum that they have to bear is only going to be for 6 years. Now, how do you hedge against such a risk? And that is where the principle of INIP comes in. The INIP's intent is for the operator, because if you go through the Act, the primary responsibility in case of a nuclear incident or an accident rests on the operator. And once, of course, our Act is different, because you see there are a number of forerunners for this Act. There is the Vienna Convention, there is the Paris Convention. When you look into these conventions, the total liability is only on the operator and never on the supplier. To that extent, our act is different. So we have to have a policy in place. We have discussed this issue with the New India Assurance Company, and we are hopeful that maybe in the next 1 month or so, the policy would be totally framed up. The intent is this, that the supplier takes a policy, the operator takes a policy, and thereafter the supplier has the facility of right of subrogation. They can pay a small amount and be ensured that the insurance company, in case there is a payout to the operator, which is NPCIL in this case, they would be protected against any claim by the insurance company through the route of subrogation. This is some of the challenges which you are facing today, and very briefly also I will mention about the imported reactors. We have had a fair amount of success when it comes to the Russians. In fact, the Russians have been insisting on quickly signing the Kudankulam 5-6. Discussions are yet to commence. And as Dr. Srinivasan mentioned, yes, the VVER design of the Russians through ASE looks to be economically viable. However, we have been discussing both with Areva as well as with Westinghouse, and to a limited extent with GE Hitachi also. The current difficulty that we face is the commercial viability part. As far as the technology is concerned, there is no doubt of it's a proven technology. It has been approved by US NRC. It has been approved by ASN in France as far as the Areva technology is concerned. So technologically, there is no issues involved. The major issue is one of commercial viability. And the main reason for commercial viability is the front loading which is being done by these international suppliers. Because unless and until you are able to sort of give us the first 2 reactors at a reasonable price, it will be very difficult for us to get into the project. And even if the project is implemented, we do not want to land up into an Enron-like situation, wherein at the end of the project you have a station whose the unit energy charges are so high that you are not in a position to sell the electricity. We are hopeful that we will be able to have some breakthrough sooner than later. And I would request if there are any questions, please.
Yes, please.
Understand that this is an administered cost almost, and which also now gets related to the tariff. Of course, Mr. Raja is in that committee to decide the tariff. So, how far the situation is there? Is it a commercial price, and since the NPCIL is the only
buyer right now.
Only buyer.
Except for small exports.
So how do you set the price of this actually? What are the principles that you would say that this is the input price of the heavy water for a nuclear station? Because this forms quite a substantial cost.
Personally, I wouldn't be able to tell you what are the
Or you would add some maybe some overheads,
I think I will try to respond to that.
Because
It is basically worked out on a cost plus basis. You see, the production of heavy water is highly energy intensive. So if you want to bring down the price of heavy water, specific energy consumption in a heavy water plant should be reduced. And that is actually happening. Because it's a distillation process where normal water has certain amount of DTO, and you're basically taking out that isotope, the DTO from normal water. So it involves first kind of fractionations followed by distillation, all of which are highly energy intensive. I can go to the extent of saying that if you go into the cost of heavy water, about 75 to 80% of the cost is the cost of energy that is required to produce heavy water.
150 ppm needs to be taken to 99.8%.
So the costing that is done internally is basically a cost plus approach. The problem which is somewhat difficult is we went through a stage, and even now we have sufficient heavy water. Yeah. That is, we are not short of heavy water. On the other hand, sometimes one feels one may be holding a little more inventory. That is calculated on the basis of so that we get a good return on it. but export is periodic. And obviously we don't want that same heavy water to go to countries which are inimical to us. So it's not that it's really exported. We have exported to China. We have
Korea.
Korea was the major.
Korea we exported more than 100 tons of heavy water. But coming to the cost question, it's a simple cost plus approach.
You see, the issue is, to be looked at this way, without heavy water, we cannot at all have natural uranium fuel reactors. The graphite option is out. And with great difficulty, this country reached a point where it has mastered heavy water production technology. And all these people like Sharma and his colleagues over a period of time, they have struggled, and the work on energy efficiency that he and his other colleagues, Hiray Math and so many of them have done is incredibly high quality. And now India is in possession of all varieties of heavy water production technology. One utilizing the so-called ammonia exchange process, the other one hydrogen sulfide water exchange process. There is yet another one, the so-called water ammonia water hydrogen exchange. So, now, no other country in the world has got all these things, and plants running, large-scale plants, safely. You know, hydrogen sulfide plant, hydrogen sulfide is a particularly vicious substance. Even extremely small quantity, you can't even smell. Before you get the smell level, the damn thing is lethal. So all of this has been really done. It's an incredible success story, which people outside the system really do not know. And it is that which has given us nuclear independence. Now, therefore, that particular commercial operation, because cost plus approach, they are not losing any money, but it's not a market opportunity. They are getting just a fair return on money employed. Now, our reactors are leased heavy water. Heavy water is held by the government of India, and then they give a lease charge and there's a small make-up charge. Now what is happening is an asset that's been created. Now when you go to this advanced heavy water reactor, after 40 years of use in the first stage reactor, the heavy water is still a precious commodity. It can go on to the advanced heavy water reactor, first of which you're going to build in the near future, but there will be many of them built for thorium utilization. So you know, the whole chain is a blessing. A tough proposition, technologically very challenging, has been accomplished. Now it's a blessing. As of now, because we are having more than 10,000 tons in inventory, but then if you want to speed up our heavy water reactor program, that is coming very handy. Nobody will sell you heavy water except in small quantities, unless you got good political equity. In fact, heavy water production capacity around the world is very limited. It's nothing to
you will permit me a liberty. I cannot help recall, I mean, thanks for the compliments that you have given, a certain meeting in which the chairman was firing us left and right. And he said because there was a shortage of heavy water and affecting the program, and I happened to react to it. It was not fair, but I happened to react to, sir, we are not leaving any stone unturned. And he snapped back, you're not turning the right stones. I keep quoting it all over the place. I think Mr. Raja, you remember, I quoted it in one of the meetings. Well, we have come a long way, and we are happy that we are turning the right stones, and we have, I might as well add a few things so that I don't have to. You see, as far as the whole program is concerned, the power program of the country, it's a very, very ambitious program what is being projected. It's a very, very ambitious program. As far as the indigenous program is concerned, as Dr. Srinivasan has pointed out, we have all the capabilities, and what has just been mentioned. heavy water is needed in quantums. I mean, make up heavy water is very little, but whenever a unit is coming up, you need a huge quantity. So it cannot be like, so we have to hold certain inventory. And as he mentioned, it's very difficult technology, and as it has happened in other countries, in the nuclear field, the field of heavy water, people who have stopped, well, all the technology has withered away. I mean, like in the US, it's, the people are not there anymore, even in the nuclear field, because they have stopped their program and things like that. Well, we are in a different phase, we are going up. And I just want to mention that for the indigenous program, it's not only the heavy water, but also the nuclear fuel complex has come a long way, and they're doing a very, very wonderful job, and there's nothing that they cannot do. It's just whatever is the PHWR program, I feel very confident that it can be done well in time, and there should be even the industry. Backup is there, but as it has been pointed out, they should have an incentive, they should have a vision. You see, the way our program is being projected, well, in 3-4 years, we want to double it. After that, in another, say, 13, 14, 15, 16, 17 years, we are almost making it 10 times. Out of which, I think the indigenous program is planned for about, addition will be about 14,000 megawatts. So for that, there's absolutely, there will be no problem, because as is pointed out, we can add to our plans, not only the inventory that we are holding, but we can add to the plans. It won't be greenfield projects. Mr. GN is here from Heavy Water. It would be an addition to the existing plant, and we have also perfected. You see the plants which are hooked on to the fertilizer plants. There we have some certain difficulties, but we can add a front enrichment unit, which is a new technology that we have developed. So with that, we can easily take care of the heavy water requirement, and NFC, I said, will be fully up to it. Also, in the atomic, Mr. Raja is aware that the atomic minerals division too has done some very good job recently, and whatever is the indigenous sources of uranium are being developed. In addition, heavy water is also taking up another route for the phosphate, taking out the rare earths from the phosphate.
Yes, yes. There are certain other activities they are doing.
Yeah.
You know, they are producing some very advanced chemicals, organic chemicals for exchange processes, all kinds of things. So, for instance, things like tributyl phosphate and something else, some other kind of stuff for nuclear people will not sell or sell at very high price. So, a lot of these things have been done. Now, you know, they very briefly put, going back to Dr. Baba, in his own time, you know, he died in 1966. The things that he did, first heavy water plant at Nangal was a decision he took, of course a small 15 ton per annum, using hydrogen distillation. Uranium, Calcutta mine, starting uranium. Reprocessing, getting plutonium out of spent fuel, and reactor designing and building. 4 keys, that is the vision. So early in the game, he said, you must have these things. And in that short period, he was only there. In 1954, the commission department was set up. 66, he passed away. In 12 years, he had got into these key areas. That, you know, his foresight, where we must put our finger and, you know. But now, since then, things have grown enormously.
So can you give some idea about actually the cost of this and the return on equity deployed?
On which one?
As was mentioned by Dr. Srinivasan, both heavy water is government property. It is leased out to the nuclear power corporation. You see, today's let's say I know the cost as it existed around 7 years ago when I was in the department. At that time, roughly broad figure was about 15,000 rupees per kilogram.
It is 16,000 is the latest one. Notified price is 16,000.
16,000.
Mr. Jain,
Per kilo.
I have something to say.
please.
This is what is the point. This is the only commodity which price is almost same for last 10 years, around 15 to 16,000.
That has come about because of the effort made on energy saving.
Yeah, that is.
Tremendous effort has been made for, as you mentioned, the special energy.
Amongst all the industries, continuously reducing specific energy consumption. Outstanding work has been done with the regulated water. Again, if I recall from memory, the specific energy consumption is something like 32 gigajoules. Am I right?
Now it is 29. Sir. Now it is 29. So almost 40% has been reduced in last 10 to 12
I
years.
the figures when I left the department.
Here must be this from the Bureau of Energy Efficiency. So at that time we used to interact with you.
I think, maybe we should organize a group, can make any people interested. I think this kind of thing they should hold and have a closed door discussions with the people interested in Bombay. And I think it's useful.
Yes, sir. We can organize it.
So I
There's a
think
request.
someone of you take the initiative and arrange for it. I mean, you don't publicize, but you educate them. Because a lot of questions arise in people's mind. And if they are explained, they will act as our ambassadors and they will then tell other people, look, people are doing a very scientific job. That's very important. So
But we need to make two small points.
sure.
You see, the other thing have already been touched upon, but I do want to mention that Dr. Srinivasan has already said that the construction period can be confined. But I would say, somebody mentioned that you can get on to a 4-year period because with new technologies, with new equipment, you can do a lot more shop fabrication where you have better control, lesser rework to be done. You can have modules, bigger modules, and with better alignment facilities are available. You can do a much quicker job because it's much easier to do the work in the shop. So you can do more and more work in the shop.
Could you shift from kind of a departmental culture to the conceptual, as far as the construction of the plant is concerned? I do not know how do you link up
You see,
supply and construction.
I'm not
in the conventional.
let me explain. You see, what is being done, I think they are the right people to speak about it because I'm not from NPCI. But it's like a question of making the packages. You see,
somebody is responsible for, you be awarding a contract.
What's happening, I think I can anticipate your question. See, right now, in some cases, Dasan Bro is doing the key area. In some cases, Godrej is doing it. In some cases, Walchan Nagar. And they are all now using absolutely top-class laser-guided alignment devices, high-capacity lifts, very sensitive jacking equipment. All kinds of things are being now done, The construction sites are no more like the old days at all. In fact, our own, part of our committee, we were there in Rajasthan, taking a look at units 7 and 8. I mean, it's amazing. It's not a true central line or no time. In the good old days, we had to do so much iterative work, because nothing is perfect according to the drawing. It doesn't come out. Actually, when you put it there and it supports and all that, you take enormous number of information and then you get the best fit to arrive at the central line of the reactor from one end to the other end, or the other perpendicular line. All these things now, computer programs. Is somebody here from NPCL construction who can tell us briefly? Yeah, the whole thing, the computer has now made such an important difference. So in the early days, I remember theodolite, they would take readings, this, that, iterate and all that. All of that is now transferred.
That part is there. This is understood. My question is that can we hold someone responsible for a project?
Who coordinates the total activity? Now it falls on the NPC.
NPC.
You are not you are not able to hold responsible for one say LMT or somebody.
No such thing.
So,
They will be held
is
responsible for
there
their
a
part.
possibility to shift that kind of a culture?
You see, unless you give the whole EPR, the complete engineering and procurement and all that, then you can hold it. But otherwise, you can also have some kind of incentive for them to complete the thing earlier. Now this brings us to a very important point, if you may permit me. I think it's very important that for our PHWR program, we take a decision, and the whole lot of it, that we are going to build so many, and a lot of pre-project activities which are common could be taken up, and that will save tremendous time in the actual execution on the site. And with now the software available for checking the interferences and things like that, makes it very much easier. There used to be old times when something, the pipe is interfering, then you wait for the site engineer, the fellow comes and he consults and a decision is given. Now it's all taken care of even before you start the site. With all the advanced technology available, I think it's a very good thing if we could take a complete committed decision, and as Dr. Srinivasan said, order out all the whatever you can order in advance, the materials. The industry also knows that these are the things coming. They can gear up. They already have certain. But I did come across certain things like L&T. They did Tarapur. That we are talking about Tarapur, and they built up certain expertise, certain people, but they disbanded it. Now, for them to build it up again, it's very difficult. So there has to be continuity in the program for the industry also to be able to take care. So the point I am making, because most of the points have already been covered by the speakers about acceptability, about liability, things like that. I would say that to me it appears that a decision has to be taken for the whole lot of program in one go. And we have to, at least for PHWR, there will be no uncertainty. For the LWR, there will be some uncertainty because of the cost and all. For that, there should be a fallback position. But 15 years or 20-year time is a very short time for plants like this to be able to bring up the capacity from, say, 6,000 to, say, 55,000, 60,000, whatever you have. So, and also, unfortunately, if I may be permitted to say, that government too should have a will, and it should not, the texture of the government changes, the priorities changes, that can hurt the program tremendously. So it should be a firm program, which is everybody's program, and if we have the attitude, can do, we can do it.
I would like to add something on the construction part of it. For the first time for Kakrapara 3-4, earlier projects, the field engineer used to be there. He used to take. For earlier projects, we used to have a field engineer cell at the project sites. They used to take care of all the interferences, and interference was reflected when the construction was going on. 9%. But there used to be too many interferences, incomplete piping, cable tray, etc. But the first time in Kakrapara 3-4, complete computer modeling, 3D modeling was done in Bombay by a company. And whatever interference was there, they were removed before the start of construction. So this has contributed drastically in the reduction of construction time. And this activity is being furthered for other projects also. So this will reduce the construction time and cost also.
I think now, would you like to make any further remarks? And we must now take both the other two speakers.
Just one small brief comment. You mentioned about the Narora fire. In fact, interestingly, it is after bus ducts was adopted by IEEE. Okay, number one. And point number two is, when we were discussing with the Westinghouse and we were looking into the cable layings as far as the Westinghouse reactors are concerned, the AP1000, they still are not compliant to the IEEE requirements. So this is the first thing that we have said, that we cannot accept any design which is non-compliant to IEEE.
Narora, DG set levels of certain auxiliaries which you had provided, including one of the CW pumps which you had, was under that flood level, which the maximum flood level which you had. And these were changed, of course, later on after our interventions from CEO on the issues. And the fire there was a serious lapse on the laying of these cables, etc. They were not segregated, and it was prone to some fire accidents. But since these things don't happen, so one doesn't care. This happens in our convention stations as well.
You know what happened even around the world? A major utility like Tennessee Valley Authority, Browns Ferry, 1,100 megawatt BWR, they had a fire. You know, early days of technology, this is the way you learn. Narora is our second nuclear project on which we did design. First was Madras, with Tarapur and Rajasthan had been done, one in the US, one in Canada. Madras was our first experiment in design, Narora was our second. So, you know, we have moved quite a lot. You're right, we can go back on it. That's where technology learning is taking place. So I think we should...
One last small question.
Yeah, please.
Because as a matter of policy, is there any thinking to upgrade or advance on the boiling water reactors rather than...
No, you know, the issue there...
What is the kind of limitations which we have?
See, the point is this, that the General Electric Company and Hitachi both actually in recent years have not had a single order. Because in many ways people have preferred to go to the PWR route. General Electric Company chairman was in India, Jeff Met. He met Mr. Modi also. After that he says, this liability issue, so far as I am concerned, is not resolved. Unless it is resolved to our satisfaction, we cannot take any risk of nuclear. So that is still the hiatus. I don't know where we are going to end up. I think for the time being, our choices are present water reactor of Indian design, Russian PWR with Russian design, Indian PWR.
So what is the return on equity?
Yeah, the return on equity is 15% in case it's on time, 15.5 in case of delayed.
And what is the life cycle?
We talk in terms of 40 years. For domestic reactors. Reactors, especially the Russian design, is again 40. But Arriva as well as in-house, 60 years.
While determining that you for 40 years or 25
We
years?
cannot do that. You also understand that financial evaluation of a power plant is on a standalone. I cannot from one to subsidize or it means it will depend upon the law. Let me give you a typical example. We have been negotiating with them. And I was to what on the OECD route. Organization of Development Countries. The OECD guideline 18 annual installment. So the total period is 25. So if I have to repay in 25, I have to also collect the. Please understand there are two elements here. One is the principal repayment and is the loan liability. And as far as since we are borrowing in foreign currency in euros, I also have to have sort of a hedging for the currency rate fluctuation. And you will also agree that in the market, the longest tenure that I is which means when I take a loan of 25 years, I am exposed to certain uncertainties as far as the currency fluctuations. So this is a very, very big risk.
Okay, so when you talk about the tariff of 0.95 paisa, so it is already expired 25 years.
It's a fully
Is your tariff constant throughout the period? Because you said
the tariff currently which tariff expired on 30th of June. The tariff is based on 5 years. Okay. And there is a committee which is constituted by the Department of Energy. And this committee, of course, and Mr. Mittal, we are all members, Mr. Raja, members of this committee. We go through the various presentations and from an independent perspective. And yes, we recommend to the Department of Atomic Energy. Once this is recommended, this is very selected by the CEA, Central Electricity. They may also give it to independent auditors to verify. Also is available to CEA in case they have reasons to look to the accuracy or correctness of some of the claims. They are satisfied with it, will give their recommendation back to DAE, and DAE in principle will notify.
Tariff after every 5-year block would go on to be pricing the tariff.
Not necessary.
Not necessary.
Not necessary. But I would say yes, it has.
It has reduced.
We said also that in a nuclear power plant, major numbers would come in after about 15 years.
So there would be a spike.
Not very appreciated. A few pies.
That will take capital investment.
Capital.
And most of your equipment, most of your projects, they all are supplier oriented. You have supplier linked on your
As far as the domestic program is concerned,
for your international.
let me tell you something very interesting. About a year and a half back, we were wanting to borrow about 2,500 crores. This is the innate strength of NPCI. So when we went into the market to borrow 2,500 crores, I had this call from EPF, Employees Fund Organization. The chairman of EPFO rang us up saying that, look, we know that you're getting into the market. Why do you want to get into the market? Because you have to pay for the, people who are going to. He said, we don't pay. In fact, NPCI does not give a single rupee to any of the arrangers. The arrangers don't pay. They said, let us do a one-to-one deal. So at TM, I was the leader of the team. We went ahead and discussed with the EPFO chairperson. And at that point of time, he offered us a rate of something like 8.56. After a lot of discussions and deliberations, he said, okay, I'm going to cut a special deal for you, 8.45. So why 8.45? We are looking at something in the range of around 8.25. He said, I just got a deal with NTPC at 8.36. And for NPCI, it will be 9 basis points more, so we will pay 8.45. So I said, why can't you give the same thing to us? He said, no. NTPC is NTPC. So I said, but size doesn't matter. Size matters. And he also gave me a threat. He said, this offer is on for 24 hours. Young man, better you accept it. Next day it will be 8.65. So he said, no, I would still like to try my luck in the market. And can you beat it? I was able to beat 8.14. I also had the cheek to call him up. I offered 2,500 crores at 8.25. So size is not always right.
In fact, 4 years back, you had also taken a line of credit from PHC. I don't know whether it was ever disbursed or not.
We never took it because it was 11.5. Yeah. I was borrowing at 8.25, 8.35.
The sanction letter was issued. You never disbursed.
Today I have 8,000 sanctioned by SBI. For the last 9 months, SBI is after us saying that if you do not at least avail of some little loan, we will cut a sorry figure before our full vote. Fortunately, the situation is fairly okay as far as the finance is concerned.
So, I'm just going to talk about nuclear energy, long-term energy security strategy for India. There has been a lot about it talked by Mr. Mittal before, so I have the pleasure of skipping many of the my slides. I think this is a brief outline of my talk, but I will allow it to its own unfold while I go ahead. Well, there are two nuclear reactions of interest for energy production. I think so far everyone was talking about fusion reaction. There is something called fusion, and there is a fusion program which India is also participating. I think we are paying a big contribution to the ITER program. So, however, I think in the near future we have to stay with fission. And when we talk about fission, the natural resources are obviously uranium and coal. The one difference with uranium is it has 0.7% fissile, and that makes a lot of difference. Thorium has none, and that 0.7% because of its presence. Uranium is a well-developed fuel cycle. We will come to know a little later. But the point is, thorium is 3 to 4 times more abundant, which means thorium utilization is important for sustainability of nuclear energy. I will also say a little bit more on the advantages of thorium. Well, I hope it comes. Yes. Well, I already said presently global nuclear energy program is predominantly based on fissile uranium-235, which is naturally occurring, but only 0.7%. All the existing reactors, almost all of them, use natural uranium or enriched uranium. Typically, our PHWR, which the previous speaker and most of the discussions was on, PHWR uses natural uranium, whereas the PWR, they use enriched uranium. But most important thing to realize is the spent fuel from PHWR typically contains about 0.4%, maybe little less or little more. That means we are only utilizing just 0.3% of the available resources. Which means typically 1 out of 300 is the one which is being utilized in the existing kind of reactor. And the fissile source is not significant. And as you know that this fissile source includes both uranium-238 as well as thorium-232. And uranium-238 is about 99.3% of the naturally occurring uranium. And if it is bombarded with one neutron, you get neutron, which is fissile. Similarly, thorium, when it is bombarded with one neutron, you get uranium-233. And as you know that India is committed to use both the uranium-238 as well as thorium-232. And obviously, not only for India, for the world, long-term energy security means adoption of a closed fuel cycle with breeding and use of fertile uranium and thorium resources. And use of thorium has to begin well before the uranium is used. Once uranium is fissile uranium is used up in the open cycle, there is no way to restart this use of thorium. Well, thorium has better physical characteristics. It is best fissile isotope in the thermal spectrum, and there are many more advantages to it. Fission to capture cross-section ratio is the highest, and the thorium U-233 bending ratio is practically insensitive to neutron energy, which means you can have thermal reactor or you can have fast breeder reactor, or you can also operate a reactor in the epithermal region. And it is also proliferation resistant, which means it is not producing plutonium, and it has got much better performance characteristics compared to uranium. Higher melting point, which means lower temperature, better thermal conductivity. Thermal conductivity means lower temperature. Higher melting point means it can tolerate much higher temperature than uranium, and lower fission gas release. There are many more advantages in the waste management. However, it has got also its own challenges. Higher melting point also means higher sintering temperature, and also it has what is called uranium-233 is always contaminated with U-232, and whose daughter products are highly radioactive, and which means we have to live with this, and we have to learn how to use this. And also there are problems in reprocessing and waste management because of this. Well, the technological options include not only fission reactors for thorium utilization. Of late, another option has come up, which is called accelerated Professor Carlo Rubbia has is talking about, the energy amplifiers. Essentially, this system is somewhat different from our existing reactor system. It has to be a coupling. It has to be a coupling of the reactor with what is called an accelerator. And this is essentially how this is being done. You have a reactor. You have a subcritical reactor supplied with spallation neutrons from which is produced because of the proton beam that is targeted on this spallation target, and these make the critical produce energy. Part of it is going to the accelerator and the rest is going to the grid. Well, it also has a advantage that you can do transportation of nuclear waste. And India is also working on this, especially the accelerator as well as the thermohydraulics, as well as there is a subcritical assembly which is for reactor physics experiments which have been recently established. Well, this I already said, reduced waste quantity and much shorter duration of storage for the hazardous waste. In the existing reactors, especially the PWRs, you have to keep it a long process, thousands of years for this waste to come back to the natural background level. But in this case, you can transmute the waste, and what is left is a short duration, and typically something around 100 to 600 years is what we need. In fact, the waste can be reduced as low level as fusion reactors. That is the advantage. And deep burning of thorium, we are actually in a subcritical stage. We can go to deep burning, much more utilization of thorium than in the existing reactors. And proliferation resistant, it doesn't produce plutonium, and also the critical mass required for U-233 is much larger compared to plutonium. And also, because of the radioactive beta emitters, gamma emitters, highly radioactive gamma emitters, this can be easily detected, if this is diverted. Also, the storage of the weapons is also going to be equally difficult task. It is going to produce radioactivity, it has to be cooled and it has to be shielded, so making it very, very heavy. So obviously, this is not the right option for the bomb. And then enhance safety due to use of subcritical system. Well, I said all this, and if this technology is developed, the other way of utilizing this, the 3-stage program may go to maybe 1,000 years for the indigenous thorium. This can take it to several million. And technologically more challenging, and which means we have to go little, and it has yet to be demonstrated on an engineering scale, although scientifically it has been done. So basically today we are left with fusion reactors, that is the immediate choice, and of course for India it is very vital because we have a large resource position of thorium, as Mittal has already got a modest reserve of uranium, and for India it is important to start large scale use of thorium much earlier than the rest of the world because of this. And of course this long term strategy requires 2-3 technological decisions. One of them, of course, is the adoption of post fuel cycle, which India has done, and use of breeder reactors. We are already developing at IGCAR, and development of self-sustaining thorium reactors. In fact, this slide has been already shown by Mr. Mittal earlier. So basically, this reactor is a well-developed one, which we call the PSWR to stage 1, and this supplies the fuel for the next stage, which will help to produce or build up an inventory of U-233, and then later on we have to have what is called self-sustaining thorium-based reactors. Today, we have asked this question: what is the reactor of this third stage? As I said, this has to be of consequence. It has to be self-sustaining. Although we start with a fissile material, but it has to be sustaining on its own with thorium. And there are several options because of the special characteristics of thorium. That is, you can have a light water breeder reactor, you can have a fast breeder reactor, and you can also have a molten salt breeder reactor, which is either in the thermal spectrum or epithermal. If you look back, the light water thermal breeder reactor, thorium breeder reactor, has already been demonstrated in the 1950s in the US. So it is obviously there, but then the problem is it has a very low breeding ratio, just 1.29% more fuel in 1 year. So which is probably is not the best option if you are looking for thorium for long-term usage. The other option is of course the fast breeder reactors. So we are in the fast breeder reactor with sodium as the coolant, which is coming up at Madras, and our own IGCAR people have done a calculation, and of course we know that metal is the best if you are using in the uranium-239, uranium-238, 239 system, and you can get the highest breeding ratio. Whereas today we are using the oxide fuel, which is having much less breeding ratio and a much larger temperature.
There are no safety issues with sodium? While
there are safety issues. Say sodium is, it can have violent reactions with air as well as with water. So sodium storing is something sodium is not new. It has been manufactured for several other industries also.
once you use it in a large scale, then like we have naphtha problems are there.
Well, the issue is the following. There is a certain amount of global experience in sodium in fast reactors. There have also been leakages and mishaps, but at the same time, there are also successful systems. For example, if we were to talk about mishap, some time ago the Americans had a reactor called fast flux reactor. The fast reactor was actually, there was a major fire and it was abandoned. And there have been leakages in Super Phoenix, French large reactor, in the Japanese reactor. They have been working for a long time. They have had a mishap. At the same time, the Russians have operated quite satisfactorily one reactor called BN350, 350 megawatt liquid sodium reactor. They then have a BN600 which is operating well. They have BN8 which is operating well. Yes, there are problems, but you can learn to live and live with them. Technology also has grown a great deal. Of course, you would think that in a sense, to say that the best material for quenching fire is water, and therefore a system that cannot accept water is a disaster. At the same time, all these sodium systems are all under blanket of argon, inert gas, and then we've got extremely sensitive leak detector systems, you've got catch tanks, backups and all that. So we are hoping our own 500 megawatt reactor in Kalpataram, which will start sometime in the near future, will probably give us good experience. So the expectation is that we can solve these problems. We would not have done it but for the incentive that the only way in which you can build a large inventory of said fuel is by going through the fast track route. If there was an option, we would not do it.
There is no alternative to this.
What?
There is no alternative to sodium.
Well, I mean, there is for sodium utilization another alternative called the accelerator-driven system that involves other types of technologies which of course are also challenging, but that also is being looked at as a long-term thing. As of now, there is a reasonable expectation that the sodium pool, liquid sodium pool systems can be made.
Okay, so also if you look at in the generation 4 itself, there is called a electrical fast reactor. Again, it has been proven. It's possible to have something without sodium, but it is said to be done.
Well, there's people talking of lead bismuth alloy as a possible coolant in some cases. But as of now, the experience of sodium is quite really good, substantial. For a long time ago, the Americans had even built a submarine reactor with sodium cooling, which had its problems when they gave it up. So the genesis is there from a long time. But, what?
Leakage would happen.
Sorry?
Leakage.
Yeah. Of course, yes. But expectations these are manageable.
Okay, coming back to this kind of reactors, if we use thorium U-233 system, then these fast breeder reactors of the type which we are using, they will not achieve breeding, even if we use the metallic fuel. But on the other hand, if we use carbide, this is going to be a breeding system. And the other option is of course the molten salt breeder reactor, which of course engage between both the FBR as well as the molten salt breeder option for thorium utilization. The one advantage of this molten salt breeder is the fissile inventory that you require is almost 4 times less, and it appears to be the best choice for the self-sustainable thorium-based reactor of the future. And if that is so, now let's look at what should be our roadmap. Of course, this has already been told by Mikkel to some extent. When we start with natural uranium, so we will have we can have a capacity factor of about 10 gigawatt if you use only the indigenous resources, and which can go up to maybe as high as 250 gigawatt if you use with a fast breeder of the plutonium U-238, and then if we build up enough inventory of U-233, and then we can go on self-sustaining reactors with thorium, and that can build up the installed capacity to very high levels.
So maximum you will go to 10 gigawatt.
No, it's only with indigenous resources. But if you are getting the fuel from outside, you can go much larger.
In the old days, the fuel import option was not in our horizon. Now that is available, so that does give us more technology options.
Okay. One thing is
there's another issue that we must not flag, more to share with people. There's a big difference in the cost of production of Indian uranium and imported uranium. Our uranium is much more expensive. It's by 4 times more expensive than international uranium. But then it's also argued that the uranium component in the cost of the final energy is so small, it doesn't matter even if you pay 2, 3, 4 times more. That's right. But now what's happening is we also must safeguard our strategic options, like we have a certain number of submarines, many more submarines that we would like to make to allocate Indian produced uranium for that kind of other issues also there.
Okay. So the issue is that we have to build up a significant level of nuclear generation capacity before we can move to the thorium fuel cycle. And incorporation of thorium in the blanket metallic fuel fast breeder reactors, when significant fast breeder reactor capacity is built up, and then shift to the uranium-233 based fast breeder reactors or molten salt reactors. And this is expected sometime beyond 2050. Now the question is, if you are telling that it is beyond 2050, Chairman has already told some time back that this is not a very fast process. So how do you motivate people, and how do you see if you see that this is the technology which is going to come beyond 2050? Today's research is very difficult to motivate. So the best path forward looks like we have to establish all the technologies which are required for thorium utilization. Well, India has already established almost all aspects of thorium fuel cycle, albeit at a laboratory scale. And that means we have started with mining, ore processing, and then fabrication of thorium pellets, fabrication of fuel, and irradiation reactors, reprocess the irradiated fuel, prepare the U-233, and then reuse the U-233 to fabricate fuel. And we have done all that, and so we have also done a few uranium-233 research reactors were also established. And present one is operating, which is called Gamini, and which is the only one reactor which is kind of operating in the world. And we also, we want to graduate from the laboratory scale to what we call the industrial scale technology demonstration, where the advanced heavy water reactor technology comes in, and both the Chairman as well as Ms. Mittal has also highlighted this. Well, this is at an advanced stage of development and can be launched in the air. This is a reactor with much enhanced safety features. Fukushima type accident happens, this reactor can continue to survive as long as 100 days without any operator intervention, with the in-containment inventory of the coolant. No need to bring in coolant from outside.
So the thermal uses passive systems, very large number of passive systems. You use density differences, things like that, natural principles. And pumping, you use thermocyclic effect, all that kind of thing across the valve operation, so on. So many areas which is not possible because no jobs are available. So that kind of thing is engineered into this age.
Like 3 Mile Island.
Yeah. 3 Mile Island, what happened is, there was a starvation of coolant into the reactor vessel, and therefore the temperature went up, and there was a water reaction of the hot water and steam to release hydrogen. There was a hydrogen bubble formed. Of course, the triggering factor was a malfunction of the valve, but although there is fear that there may be an explosion with that hydrogen bubble formation, no such explosion, and they were able to keep systems cool enough and avoid a major catastrophe. And therefore, you can say, yes, catastrophe was avoided. In the system that they operate in, the utility owns that reactor when time. There will be some evacuation and all that, but it didn't happen. And in fact, Jimmy Carter, who was a submarine reactor engineer entirely new technology. That is how to manage severe accidents. This is an evolving picture. One theory is, well, if you are managing a severe accident, you may in fact commit a slightly higher exposure to people near there and save the trauma of moving them out altogether. Another theory is, no, you play safe. We are still looking for this. But I think, considering statistically speaking, the number of accidents is still very small. Hopefully they will be even smaller statistically. So I think that should not, many people had fear post-Fukushima moratorium on nuclear power altogether. View for internal political reasons to retire the reactors and not build anymore. Whether they will stick with that or if it is another matter. But the Americans, the French, the Koreans, the Russians, the Chinese and Indians, they all felt that no, I don't think we should take a drastic view and then it's rather more like in the aircraft industry. Yes, there is a crash. Unfortunate, you learn how to build, you improve the systems, you improve the design, you improve the operating regime, you improve the maintenance regime, diagnostics. Yeah.
Okay.
How much more time do you want?
Maybe another 5 minutes.
Good, please.
See, this molten salt breeder reactor is the most suitable candidate. It appears to be at the moment for the third stage, and it is a high reactor, which means you can generate electricity with high efficiency, and it can also use
supercritical.
No, I think, well, in principle, these reactors have certain reactivity which is, which K can be like effective multiplication factor is slightly more than 1. But there are enough controls and enough shutdown systems. If it exceeds a certain level or certain value, then it automatically.
No, I think the question is in a different sense. He is talking about the power conversion cycle.
Oh, this can
part of the.
Yeah, this can use not only
use the saturated.
this can say nuclear reactors with the exception of a phosphorated type which we are using
Since you were saying temperature is high.
Yeah, so nuclear reactors normally use the saturated steam with the exception of a phosphorated reactor which is using the supercritical steam. However, this reactor you can switch to supercritical, you can go to ultra supercritical, or you can even go to the advanced supercritical because the temperatures are such that you can even go for hydrogen production with the sulfur process which needs something around 850 degrees. So this will generate an exit temperature of about 900.
Of course, one thing you have to bear in mind, long ago some experiments were done in Oak Ridge in the United States. But you are dealing with offensive salts. This is also very aggressive. Materials of construction are there. Like this behavior of these molten salt with the construction material. It is a technology, but again, so much more knowledge is being gained on alloy materials, methods and so on. So it's an option available. There are a lot of work needs to be done. That's what he's making.
The worldwide is
No, this, as he himself said just now, it has been demonstrated at Oak Ridge National Laboratory, and they have even designed reactor for 1000 megawatt electric. But what demonstrated is a small scale, 2.5 megawatt, and just basically a thermal physics demonstration. So it has run successfully over several years, maybe 4 or 5 years it has been run. And they also developed a new material for using the S2N was essentially developed for this reactor. Now it is.
S2N is used in
now it is
high temperature equipment.
Now it is used in many industries, but originally it was developed for this reactor. S2I, it is called. Well, the strategy for generation. Well, the most important thing, if you want to switch to pH or the molten salt reactor, what we need is U-233, which means we need to have a strategy for generation of uranium-33, which means means, so obviously this can be generated in the reactors. See both the PSWR or the proposed PFBR as well as the existing fast reactor. And there are several options which we have studied. And different options produce different quantities of the U-233. And if we can take one PHWR, well then you can switch to, I think it is yeah, maybe I will continue. So there are different options. Some of them produce more U-233, some of them produce less U-233. But if we dedicate one or two reactor stations which are outside the safeguard to produce U-233, then we can generate enough U-233, as you can see here, for start of this molten salt reactor, even in the early 20s or maybe mid 20s. And if you look at, we can also produce U-233 using the fast test reactor, which is being done at the moment. We are using 9 to 12 rings, so which can only give us 23 kg in 5 years. Oh, sorry, in 5 full power years. And if you also use in extra thorium bundles, then you can get this. On the other hand, if you use it in fast breeder test blanket, it is.
Can you give some idea of the specific
You mean because of use of this thoria in the reactor? Yeah. For example, if you go to this option, see it is basically producing much less fuel, but it can be directly done. But there was some extra natural uranium that we use in this reactor, which means if NPCI can be compensated for the additional natural uranium which they need to be used, then we can do this production. And also, this needs what we call slightly enriched uranium bundles, and this can also be done. But of course, we have manufactured this slightly enriched uranium bundle, and then this one basically. If we are using thorium plus plutonium in the entire reactor, then we can get much higher tolerance. But all that is possible only if some stations are dedicated to this.
What time would you like?
Yes. Well, we said the thorium molten salt reactor is a self-sustaining option. We have already made a conceptual design, and if you can see that this has what we call online removal as well as protactinium removal. It actually enhances the neutron economy, and we will also the breeding ratio significantly more than that in the fast breeder reactors.
Laboratory is modular
in India, but the reactor which was demonstrated in Oak Ridge National Laboratory without this online reprocessing option. Otherwise, other options were there. And then this the other advantage is it is a low pressure system, and because the molten boils at around 1470 degrees Celsius, so you can even operate them up to 1000 degrees centigrade, provided you develop the materials for this one. Hydrogen, this is another thing. See, we talked about Fukushima and the 3 Mile Island. There were some hydrogen generation in 3 Mile, whereas in Fukushima there was an explosion which actually made the containment, almost destroy the containment. Whereas these reactors will not produce hydrogen, and the core is already molten, so there is no salt will boil only at 70 degrees centigrade. But what we are planning to operate is something around 900 degrees centigrade. That's the maximum.
The materials, etc., which you propose to use, would they be designed for boiling?
One advantage of this is only the your power conversion system. See, what we plan to use is what we call the vegetable, which is based on supercritical carbon dioxide. So this system is the only one which is high pressure, whereas the entire system is at low pressure. So the advantage is, although some of these nickel-based alloys which we are talking about, Inconel 617, they can at these pressures they can see temperatures as high as 900. However, we must establish a demonstration unit and generate operating experience. And there are less complications in, we mentioned there is this U232 which ultimately gives up very high gamma emitters. And in case of a solid fuel fabrication, it's a big problem. You have to make a remote fuel fabrication facility with a lot of shielding. But in this case, it is a chemical plant, so you don't have that issue. And also, you will find it doesn't need any water anywhere. So the advantage is, you can existing reactors, either they are on the coast or a big water body where there is, the surrounding land is very farmland. So this reactor can be located where absolutely there is no water. It doesn't need any water. Well, the challenges, yes, of course, there are challenges. We have to analyze all these systems. We need electronic codes. Current electronic codes, most of them are not with the fuel movement. So and as well as we have to incorporate what we call the online fission product removal, and these are all to be incorporated in this code. And other things like large scale salt verification, these are all being done. See, our chemistry group is already working on these things, as well as this physical property characterization, and we are currently studying experimentally some of these loops with cotton salt. Some of them has already been operated. Also, physical compatibility studies, we have established facilities. So things are in line. And as I said, what needs to be done is development of enabling technologies, which is, have listed a few of them.
Because reactor development ignores all these things.
Yes,
so.
yes.
Maybe we can just wind up with a few questions, you think?
Yeah, I think yes.
Oh, you got his concluding remarks, yeah, please.
Which means, okay, that leakage in the nuclear power program definitely provides long-term energy security for several centuries. However, industrial scale technology demonstration is required, and molten salt breeder reactor seems to be the most suitable candidate. And obviously, if you want to start it in the mid-20s, then we need to start producing U233 right away in this PHWRs. And major challenges include online reprocessing, protactinium removal and storage, as remote fuel fabrication sheet replacement.
I think interesting. Of course, in all these things, issues that arises in policy making is the judgment on where the limited amount of fissile material that we will be having a surplus to use best, in which part. And of course, one of the issues that political, when I say political, public perception level, everybody says, let's go to thorium tomorrow, let's go to thorium tomorrow. But it isn't that simple really. You need to go through a whole host of developmental tasks and intermediate phases, technology development, material development, all those things. Plus, of course, management of the cell materials. In our case, only apart from uranium-235, how we use it and launch the next day is a very important question. But I think that a bit later as we go along, the interesting point is the most optimal path for the longer term. Now, I think we just take another 10 minutes for any general points, brief ones, and we should conclude in about 10 minutes. Please. Well, sorry. Answer to that, I think after Fukushima, that was a commercial as a dream, because the risks involved with private sector power, nuclear, are such. In the end, they will expect the government to pick up all the risks. So you see, this was thought of as a mechanism to bring in more investments, but you will find that concluding agreements of that kind of horizon, with NPCIL playing the lead role, with the options of PHWR, VVER, IPWR, and then the middle term option of fast reactor and the thorium-based systems. The private sector will come, let's see, but don't burden yourself with that, and don't be another wild goose chase. You'll be spending a heck of a lot of time, because the private sector will want protection from all kinds of risks. That's briefly put. Yes.
I was saying this thorium,
he already gave a very good answer, 2050 and beyond. Well, we can have the first HWR, it can be in 2028, 27, yeah. We may even have a MS, the molten salt system possibly in 10 years. We can have. We'll have some amounts of thorium rating to do to 33. But all that is required is preparatory activity. But large scale energy from thorium, not much before 2040, 2050. Yes?
That is another question regarding private participation. You had a joint venture with NTPC. So can you throw some light on that? What is the advantage?
Yeah.
What advantage will both companies and to India as a whole? How this will be benefiting?
The intent of forming this joint venture was also to spread NPCIL's finances slightly, in the sense that NPCIL has got a financial resources arrangement. It is surplus. So the intent was that in case there is a 49-51 partnership, the 51% being the NPCIL, to that extent, NPCIL can sort of invest in another project. Main challenge which we are facing today, we have a valid JV arrangement. There's a company which is functioning. Unfortunately, the Act happens not to define, because under the Atomic Energy Act, production of nuclear energy can only be done by a government company. Okay. So yes, whether this will qualify as a government company was the interpretation which has been given by the lawyers. To qualify as a government company, the shares has to be held for and on behalf of the President of India. When you talk in terms of JV between two companies, the shares are held on behalf of the investors. The investor here is NPCIL. So the equity issuing is in the name of NPCIL and NTPC. It's not in the name of President of India. So there is a move to amend the Act, and hopefully it will come.
This is taking far too long a time. We were keen on moving ahead, but in the Indian system, Parliament never does any business. And then they say once you go this way, they say go that way. The Companies Act, the Atomic Energy Act. It is a high test is there as in so many other areas. Yeah. Any other burning question from somebody?
Sir, how to anything happen in nuclear reactor? Because we have n number of suppliers. They are supplying so many components. How to fix a responsibility?
Can you briefly answer?
Yeah. It's a very challenging question, not interesting, but more than interesting is challenging. You are aware that in any nuclear reactor, one single component by itself cannot cause a nuclear incident, forget about an accident. Okay, so in case there is an accident and for which it is notified under the Act and for which compensation has to be paid. Okay, if you go through the rule, Rule 24, NPCIL has the right to move ahead and sue the suppliers. This is also under Section 16D.
but the fault is to be attributed to that.
Yes,
particular
so you have to
supplier.
do a root cause analysis.
Yeah.
How is it to be apportioned? That's his question.
Apportionment. I already mentioned in my small discussion that suppose we are able to focus and say pinpoint and say this component caused the failure which led to XYZ. Okay. And the value of that is limited to say 10 crores. The maximum amount that can be claimed from him is
The
10
extent
crores.
of that.
Yes, but we are also trying to cover him up through the INIP, that is the insurance policy, to that extent, through the route of subrogation. Subrogation means NPCIL will pay that amount to whomever it is claimed. Insurance will pay NPCIL. However, the insurance agency will not sue the supplier.
Good, very good answer. Anyone else? Well, otherwise I would say it's been a very interesting session. I think all the panel members have done a fine job. I think we also had very good floor participation. So let me say thank you for all the panelists, for the audience participation, and then wish you a good lunch.
Thank you.
I should take the